Hello, this video is on the dot product, and I'm following James Stewart's calculus textbook. This is in chapter 13, the third section. Now, you may know the dot product from physics. In the physics book and the set of physics videos I've done, the dot product is actually used in the very first chapter. So it's kind of funny. Here we are in the 13th chapter of a calculus textbook doing something that we do in the first chapter of a calculus book. Of a physics book. The thing is, however, this calculus textbook introduces it in a much more rigorous way, and I actually think the physics way is much easier to get your head around if you're a kind of a practical kind of person. So imagine that you're pulling a wagon. This is the physics way into the dot product, and you're pulling on the wagon at this kind of angle, theta, from the perpendicular. Now, these are two vectors, so you're pulling at it in a certain direction. That's a force. It's a magnitude with direction, right? And so the force with the arrow over it is a vector. And then displacement, distance, you can have a distance in any direction, but let's talk about displacement as a vector, meaning that it's not just a distance, but it's a distance in a certain direction, namely in this horizontal way. So we have a force and we have a direction. Now, you may know from physics, or you may not, that work, the amount of work done, one way of talking about work in physics, is force times direction, which makes sense, right? How much work did you do? Well, I pulled with this force for this distance. Now, the thing here is that the force is at a different angle than the displacement. And so thus we have what's called the dot product. Work equals the dot product of the force vector and the displacement vector. Now, work is not a vector. Work is a scalar. We just say, bleh, you did that amount of work. And so the dot product is not a vector product. It's a scalar product. Now, if you think back, what have we done in this chapter 13 in James Stewart? Well, we've done vector addition, and we've done vector subtraction. So now in this section, we're asking, what is it like to multiply vectors? Okay, so the dot product is a multiplication of vectors that results in a scalar, just a magnitude. Now, the next section after this one is the cross product. That's the vector product of two vectors. But this section, this third section of the chapter of 13, is the scalar product. That is just a magnitude product of two vectors. Okay, so you can see how this would work, right? You're going, because the cosine of this angle is this. So if I want to know what amount of the force is going in this direction, then I'm going to multiply the force times the cosine of theta, right? Because the cosine of theta is the adjacent over the hypotenuse. And so if I multiply the hypotenuse by the cosine of this angle, I'm going to get the amount of the force that's going this way. So you can see that the dot product is the amount of force that's going this way times the displacement. Okay, how do we write that up? This is how well, first of all, let me just say some things I've already said. It is a scalar product, sometimes called an inner product of two vectors. It amounts to the magnitude of one vector times the projection of the other vector on it. I'll talk about projections in a second, but basically, if I project this force on this, in other words, find the component of the force going that way, I'm going your way, that is what it is. It's the magnitude of one vector times the projection of the other vector onto it. Okay? So this is basically how physics thinks of the dot product. The dot product between two vectors is basically the magnitude of the one vector, absolute value of one direct vector, times the magnitude of the other vector, absolute value of the other vector, times the cosine of the angle between them. AB cosine theta is the way of doing the dot product. And this makes sense. Giving you a practical example, you can see, aha, that's how it works. Or if we want to rearrange things around, the cosine of the angle equals the dot product divided by, the absolute values of the quantities. Okay, got it? That makes sense, right? Now, of course, we can't end there. We've got to, this is a 13th chapter of a calculus textbook. We got to make things hard. So let's go on to this question of projection. So this is the vector projection of A on B. And so if I take the vector A and I project it onto B, this is the vector projection of A on B. Why is it a vector projection? Because it's going the same direction. Or we could do it the other way, or we can vector project B on A. Perpendicularize it, and then we've got the part of B that's going A's way. So that's the vector projection of either A on B or B on A. And the way we write it is the projection of A on B or the projection of B on A. Okay? There's also a scalar component that is COMP of B on A and so forth. I'll talk about that in a second. Okay, so I thought that it would be easy. I'm doing things out of order in this section from what I consider to be the easier part of the section to the harder parts of the section, or the more abstract parts of the section. So this is the basic idea of what a projection of something on something is, a vector on another vector. Okay, now here's the math definition. This is the one that the section opens with. Now, I don't know, maybe when I was in my 20s, I would have thought, yeah, this is perfectly sense. Maybe I've gotten more practical in my old age, and so I want to come in through the physics door. But here's the math definition of a dot product using, again, this nomenclature. What is this nomenclature? Well, let's try to remember what we've done so far in chapter 13. A1, A2, A3 it's not exactly the X component, the Y component, and the Z component, but that might help you. It helps me remember it. If you take a vector A, and if you were to take that vector A and you were to locate it at the point of origin of a coordinate system, then that would make A the amount X and B the amount Y and A3 the amount Z. If you were to take the vector wherever it is and were to center it as if it was coming out of the point of origin, then A1, A2, A3 would basically be the X, Y, and Z components. Now, if it's not at the point of origin, then basically it is relatively speaking, how much over in the X direction, how much in the Y direction, how much in the Z direction. The same for B. So these are two vectors here, three-dimensional vectors in this case. Could be A1, A2, a two-dimensional vector, but we're in the 13th chapter, so they're going to give you a three-dimensional. And of course, as you'll find out when you go into linear algebra, I think that you can have n number of these. You can have dimensions beyond what we can comprehend visually. Okay, so the dot product, what is the dot product of these two vectors? Well, it's going to turn out to be the first times the second, the first times the first, the second times the second, and the third times the third. And then you add them all together. I tried to make sense of this in my mind. And it basically, you're finding, again, it's a scalar product. I mean, it's a scalar amount that comes out. And so it doesn't surprise me in that sense that this is just a quantity. There's no direction to the result here. And so we don't have to worry about what direction it's going in when it comes to doing this. But we're basically multiplying the similar components of each vector times each other and then adding it all together. And this comes out exactly the same as what we did with the physics approach. AB cosine theta comes out exactly the same. But this is a way of doing it in a more abstract kind of way. So here's another thing that you should know is slipped into this chapter. Two vectors are perpendicular or orthogonal if and only if their dot product is 0. Why would this be the case? Well, because B1 is going to be 0 in relation to A1 if they're perpendicular to each other. Same thing with these other two, that if these things are completely perpendicular to each other, then relative to each other, one of them is going to be 0 in every case. And so basically the whole thing's going to add up to 0 if it's perpendicular or orthogonal. And that language, again, is important in linear algebra. And I know in quantum physics, orthogonality is an important concept. So tuck that away somewhere. And again, ours is not to question why when we don't understand. Ours is just to memorize or die. Okay, so what are the properties of dot products? Well, they turn out to be pretty normal. If you multiply, if you do a dot product of a thing by itself, it ends up being the square of itself. This commutative property works for dot products. The associative, or actually this is distributive. The distributive property of dot products works. This is distributive, I believe. Yes. And then this is the zero property, that if you do a dot product of anything with zero, it's zero. Okay, nothing to write home about there. Okay, direction angles. It's a little hard to draw. This is meant to be three-dimensional, so we have the x-axis, the y-axis, and the z-axis. So the x angle alpha is basically, and it's hard to see, this arrow was meant to be out a little bit. It wasn't meant to be in the YZ plane. You could interpret this to be in the YZ plane. I meant for it to be out, and I drew this little triangle to help you to see that the vectors coming out a little bit. And so the alpha angle here basically is the angle going directly from the x axis to whatever the vector is. And then so the y component here, or y angle, direction angle, beta, is going to be from the y-axis to the shortest distance in an angle to this vector. And then the gamma is going to be from the z-axis to that vector. So these are direction angles, alpha, beta, gamma. And direction cosines are associated with these angles. So basically, A1, the A1 component divided by the vector is going to be the cosine of alpha, and then the A2 vector divided by the overall vector is going to be the cosine of beta, and then the third angle divided by the overall vector is going to give you the cosine of gamma. Again, if you think of A1 as being kind of like an x component, and A2 as being kind of like a y component, and A3 is kind of being like a z component, then the cosine of these angles basically, it's again that adjacent over the hypotenuse. The bottom is the hypotenuse, right? And this is the adjacent. So each of these is the adjacent over the hypotenuse, as it were. Okay, more on projections. Remember I talked about how in my diagram, I talked about the vector projection of B onto A, projection of B onto A. The scalar projection is basically the same thing, but without the direction. And we're going to call this the component of B onto A. It's the same thing, it's just without the direction. Now, the vector projection is the scalar projection times the unit vector, which unit vector ijk indicates direction. And so it's a unit vector, so it only has a magnitude of 1. So all you get when you multiply something by a unit vector is you're saying, and let's take the direction into account. And so basically, you can see that it's the same as this, except we have put in the final vector to indicate the direction. But of course, a divided by a squared ends up being just 1 over a. So this cancels out. In terms of magnitude, these two cancel out. But the dot product is a scalar, and the absolute value is a magnitude. So this ends up being a scalar. But here, because we're multiplying by the vector, in the way we're talking about it, it ends up being a vector. Okay. Have I confused you enough? I know I'm confused. Okay. The law of cosines, I thought I'd slide this in here because I don't remember this. I must have known this at some point when I was in high school. Maybe I didn't. But I thought this was really neat, and it's mentioned in one of the proofs in this section. So this is an appendix. So the law of cosine basically says, if I don't, now this is not a right triangle, so it's not a simple a squared plus b squared equals c squared. But how do I find c in a situation where I don't exactly have a right triangle? And so what we do is we pretend like this particular corner of the triangle is on the origin of a coordinate frame. And then if a triangle has sides with lengths a, b, and c, then, and theta is the angle between sides A and B, then c squared equals a squared plus b squared minus 2ab cosine theta. And of course, in the appendix of James Stewart, page A33, one of the assignments is to prove this, which I'm sure I could do, but I'm not going to take the time to worry about it. So you recognize c squared equals a squared plus b squared from the Pythagorean theorem. That would be the measure of c if this were perpendicular, right? If this was a right angle, that would be the case. But it's not the case. And so I have to subtract some. And the subtracted amount ends up being minus 2ab cosine theta. I thought that was neat. You learn something new every day. Not necessarily, but sometimes you do. Well, this has been the dot product and a very long video. Sorry.